Dietmar Kuhl is the only person in the room that has been in the committee more time than me, meaning that I've been in the committee like 16 years now, and when I joined the committee, he had been there for more than a decade. So you owe many, many things of the standard, only the good things to Dietmar. And he is going to talk us about asynchronous C++. So I have nothing else to say for now.
Okay. And resume later, I guess. Yes, yes. Okay, hello, I'm Dietmar Kuhl. I work, as one might guess, at Bloomberg. I work also on the committee since 1996. First committee I attended was in Stockholm. It was lovely. People said it was a good way to learn about things, so I came back and kept going. The talk. I hope this is relatively basic. And there's something I realized with my last couple of talks. I'm talking about asynchronous C++ since a while. And the first thing I talked about, how do you implement things in the basics and how does that look like? This is how I understand things. And then I explained how would we do coroutines, how can we implement a coroutine, which is in the async space, which is kind of a little bit higher level, and then I showed how to implement something like that. But actually I realized that I never really talked about why are we doing any of that and what are the basic concepts of async to start with. And maybe get rid of that. So all in all, I may have given the talks entirely in the wrong order. So at the end, I reference all the other videos. One was taken 2 years ago over here, the other ones, and CPPCon. Maybe it may be interesting to watch them. Okay, so why I'm interested in this stuff at all at the moment, C++ 26 adds std execution, which is, in my mind, a huge deal. I know people are all talking about contracts and reflection. It doesn't matter. Nobody cares. Right? In the end, you need to execute things, and you need to execute things with the proper resources, and that is where all the async stuff comes in, and I hope to explain that. So this is why that is important, or the other stuff is whatever. So what is being added is actually kind of, unfortunately, only things which are kind of the low-level basics to do async work on top of it. It's again something which we standardize, which is actually not readily usable unless you take something else. It basically gives you the infrastructure to do things, it gives you the vocabulary, but it doesn't give the actual implementation. There's a lot of nice tools, but there's no async work. So this is important to me. Let me try to explain why we are doing that. So why do we do asynchronous at all? And my first reaction was kind of, oh, yeah, trying to explain that. And I came, well, what is synchronous anyway? Like if you look at what a computer does, there's hardly anything which is actually generally synchronous. Yes, there are some things when you write a small algorithm which actually doesn't take any I/O, doesn't take anything, maybe that is synchronous. But the moment you touch a database, the moment you touch a file, you touch I/O, none of that stuff is really synchronous anymore. The moment you go and do any kind of I/O or you talk to a different CPU, you kind of, well, the current CPU cannot carry on. It's kind of done. Interesting. And it kind of waits for other things to happen. So in that sense, yes, there are some synchronous stuff. Most of the time, this is, sure, if you do really just compute stuff, but actually if you're really interested in compute stuff, It turns out you probably want to have not just one CPU. You may want to talk to a GPU. Maybe you want to talk to actually a whole cluster. And then you are asynchronous again. Right, sure, the basic blocks you actually execute over there will be synchronous, but the overall problem is mostly asynchronous. And it's really embarrassing that we have come over many, many years of C++ and don't have an abstraction for that. Asynchronicity in C++ or in any programming language is not new at all. Right? So who has done anything asynchronous in C++ or in C or anywhere? So quite a number of people say yes, which is kind of cool, but probably the approaches to do that were somewhat ad hoc. And if I give you a library which does something asynchronous and you give me your library which is doing something asynchronous, there's probably some kind of mismatch with how they work together. And this is what we try to fix over here. Okay, so instead of saying, right, was synchronous at all, let's talk a little bit more about what actually is really obviously asynchronous. Like the moment you have, for example, user interaction, right? The user just sits there and they press a mouse, for example, or press something on a keyboard or wiggle, use one of these devices, whatever it is. This is kind of, the CPU has nothing to do while the user is not doing anything. On the other hand, you probably don't want to have a program which goes and says, oh, okay, now I wait for a keyboard click. Because while the CPU waits for a keyboard click, like if you don't do anything else, the program is just stagnant and doesn't do anything. This is not the programs we have. Maybe you have a time which clocks up. Well, this is some other processing. So you cannot wait until somebody clicks a keyboard for the time to update. I mean, some people are around my age or older even. Yes, we have seen programs like that in the past where you actually needed to press a key for something to happen. This was a real thing, but we have moved on for that. So this is obviously something which asynchronicity could help us. The idea of asynchronicity over here is the CPU does something until you need something, and then the processing stops, and later we resume somehow where we left things off. The alternative is use multiple threads, which comes with all the problems of threading, and for something like waiting for a keyboard click while updating a time, that is a little bit shooting with really big guns on a really small target. You don't want that. This is just adding a lot of complexity for no good reason. Another place where asynchronicity comes in, this is what I see at work a lot, is basically servers. If you have a process which processes something, well, a server on one CPU with sequential processing, you can do it, but you basically can only deal with one request at a time, with one outstanding operation at a time, assuming you have one thread. Again, you can solve that with multiple threads, but do we really want to have multiple threads just because we want to wait for clients to connect, to then ask a database, we wait for the database to come back and respond? That doesn't really make a lot of sense. You can spawn one thread per client if you want to. It technically works to a certain limit, but you get all the threading problems. So servers is a typical case where asynchronicity actually helps you. And if you want to go to serving many, many clients, this is where asynchronicity really helps. Threads is an interesting one, right? Assuming we have many threads, you still have asynchronicity. This is basically the place where you synchronize on things. You do something and eventually you get a result, but the result is produced by multiple inputs, and you basically need to wait until everybody is ready, for example. And then you can do something. This is the asynchronicity part where you go, all right, we basically compute something until we are all done. And there's some synchronization, but you don't do that synchronously. You don't sit there normally with a thread waiting for other threads to finish. You typically go, yeah, my thread should do some work in the meantime as well. So these are all examples where asynchronicity comes into the world. Now, once we have that, and then the other part is, which is actually kind of important to me, most people over here probably have created a program at some point, but most of the time we create actually libraries. Like, let me ask a silly question. Who has created this year, like in the last 3 months or something, a main function which is going to production or has gone to production? Anybody created a new main function where someone created a program? Wow, some people do that. That's amazing. If you ask me, when did I last create a main function on the software I'm working on which went into production, I would go, actually, this is probably a decade or more ago. I normally write libraries. I normally write things in which are basically composed into other things. Yes, I work effectively on a program which I refine, and it's basically I build one part of a library component which has a main. It has a main, yes, and we deploy that. But I normally don't do that. Now, if every library has their own idea how they want to deal with I/O, how they want to deal with threading, you actually end up with programs which have often a lot of thread pools, each one with many threads. And then you look at what's going on my machine, and nothing happens over there, but there are hundreds of threads running. It's kind of, why are there hundreds of threads? That does not make any sense whatsoever. And like a simple use case, like I just want to have a request response server to do something simple, and it's not really performance critical yet. I don't have thousands of users. Why would I spawn threads or any of that? A library for that should not impose a model how to do these things. But it probably has asynchronicity in there because, as I said earlier, what is synchronous at all? Most of the things are actually asynchronous. So it's really embarrassing that we don't have the abstractions, and a lot of our libraries actually have asynchronous components, may have a thread pool, God knows what they have in there, but they have no asynchronous interface. Or if they have an asynchronous interface, it tends to be ad hoc and specific for the library. So this is where common interface comes in. Another reason to deal with asynchronicity, actually, where you run out eventually of threads, is you can actually use a lot of threads. I had hoped that I could create a nice demo where I just spin up lots of threads and show that running lots of threads is actually bringing my machine down. I didn't manage to do that. It kept me at, I couldn't create more than 2,500 threads. That's where I stopped. And when they don't do any work, they're actually not impeding the system at all. But the system has a limit of threads it can create. It doesn't have or it has a higher limit, or you can set it to a higher limit of network connections. So if you use asynchronous approaches, you can actually respond to more network connections than you could do if you used threads. This is now on not a server machine. I don't know whether it's different on server machines. I haven't tried that. But the overall resources used for an asynchronous approach tend to be much smaller than spinning up a thread. Because, as we will see, the idea of an asynchronous thing is you actually, while the thing is waiting, it has basically just the necessary data to contain what you're going to carry on with, roughly speaking, rather than having a stack, rather than having all kind of execution resources, or kind of whatever I may need to have for a thread to be restored. I need to remember all the registers and GPU registers and God knows what. Okay, so let's talk a little bit about asynchronous basics, because independent on how you do asynchronously, there are some things which are actually common, as far as I can tell, to all the models we do. And basically what it amounts to is there are a few ingredients. The first thing is you actually represent how the actual work. Now, in programs, typically we call a function, and this is how we represent work. This is a function, but a function is kind of ephemeral. In many asynchronous systems, you actually don't represent work as a function call. Rather, you represent it as an object, which does things. It represents the parameter, which doesn't necessarily do things yet, but once you start executing it, this is the work you want it to do. And it basically doesn't execute by its own. You need to start it eventually. And this is the other part is you represent the work, and at some point, potentially later, you start it. And then once you have started things, something happens, whatever that is. I will go a little bit more into detail how that could look like, but something happens to eventually complete the work you wanted to do. For example, maybe you want to wait for a network connection to come in. What that means is when starting the work, the asynchronous thing goes typically to some kind of I/O context and says, oh, can you please tell me when there is a new connection on this thing? And the completion consists of, yes, here's a new connection, and this is a connection thing. And this is they then later resume. So you have basically start the work. While the work is going on, the corresponding thread can do whatever it needs to do, and eventually something resumes the work where you need to resume. So it's basically multiple stages, and the important part of the asynchronous here is you start the work, you don't care about that, you do other work, come back eventually once it's completed. And you can have many of these, they can interleave, you can have things being started and other things being started which then resume before the other one resumes, whatever. There's a lot of unpredictability in there, but it's reasonably, or can be reasonably structured. So the obvious example, everybody wants to serve cat images, right? What else would we want to do in our spare time rather than serving cat images? There's an entirely synchronous way to do that. Right? We basically await somebody coming in, a client telling us, all right, I want the image of that cat, and unfortunately I'm not good at doing images, so you won't see actually any cat images. I just haven't created that server or loaded it with images, but I could. So the idea is we ask for, the client says, all right, this is what we want, and then we basically read the resource which is requested. This is a very normal response, request-response service, right? Whether it's actually serving cat images or does a database request or does a computation, whatever it does, right? Somebody tells us what we do, and eventually sends a response. And this is entirely sequential. If we wanted to execute multiple of these things, we would need multiple threads to do that. So this is the three places where probably time passes between we want to do that, we want to receive a request or we want to read a file, and we want to send a response, and before we actually finish any of these things, time passes in some shape or form. Something does work in the meantime. Okay, so how does it look like in an asynchronous world? So the basic idea is when we do something like a receive request, we typically have some kind of a client entity which identifies this is where we want to get a request from. And for now, this references this big black box. I will later show a little bit about how the big black box looks like. But conceptually, there's a big black box. We don't care what is in there. And we just know about it. Right? The client knows about it. It's basically, when you create a connection, it has a connection to an I/O context in some shape or form. When we ask the receive request, if we execute that, if we start that, we basically have a receive operation, which basically knows about the connection information. This comes from the client. This is sort of the socket handle, file descriptor, whatever this represents. And the other part this needs to represent is how do we complete? There can be an entity where we complete. And then when we start that thing, we tell the the black box, all right, here is our receive operation. When you're done with the operation you started, please call into that. And then the request can go away. We don't know about that anymore. The black box knows, all right, I need to serve that request, and here's how I carry on. And then eventually, the completion, the black box can forget about the connection because it says, all right, here's the completion, and we can complete the with basically starting, all right, we found the cat name and go on to the next step. So this is basically how received request works, and there could be time passing in between and can take whatever it could do if we made it asynchronous. So we basically need to change what we have over here, which is synchronous formulation, into something which makes it viable for asynchronously. And all we do is from going from a sequential one to, all right, let's do a completion over here. This is not the standard interface. This is conceptually representing how that would look like, right? Effectively, we do a request and eventually we call a function. In this case, we carry on doing something sequential still. This is not interesting, so we basically do the same thing. We replace the read file with a asynchronous version where we basically pass in the result instead of returning it. And then likewise for the send response, we basically go, right, we complete over here. At the moment, we actually don't know where to send that, or what we do once we have sent that. This guy basically terminates over here. This is, by the way, how often things are implemented. If you basically have kind of a single shot thing to basically drop the last completion, but actually having the last thing complete as well is really valuable. The reason this is valuable is, in the end, you can actually arrange for something which started something else, so basically a bigger work which started sub-work, to arrange that the outer work which started any sub-work only completes once all sub-work is completed. That has the interesting effect that any state you can actually keep in your outer work. You don't need to have a shared pointer or something like that, which is reference counted until nobody is caring about it and stopped on the floor. You can actually just say, I have one outer thing which has all the state or hangs on to all the necessary state, and once everything completes and the outer thing completes, then we let go of the outer thing. So you have only one entity for kind of new work you need to maintain. I will get back a little bit to that later. Right, so this is basically turning the original function into one which is more asynchronous friendly. We will see to do it differently a little bit, but conceptually this is the idea. We basically just separate these things. Now, I mentioned that the work basically is represented as objects. The nice thing is, if you actually represent work as objects, you can hold on to them and you can compose them and basically aggregate bigger work before you actually start anything. The reason you want to basically compose things and start things only once you have everything composed is you avoid any asynchronous issues building your work graph and dealing with the fact that while you build the work graph, things may complete already. If we basically started things right away, eagerly, we go, all right, let's start work immediately. And then do other things and we chain them on. You may get into the stage where you're still composing your bigger work while things respond. So you need synchronization in some shape or form potentially, assuming you actually run on multiple threads. Okay. So, and I will show a little bit of things what I mean with composing work where it's actually kind of nice to do that. Although, here's an example how we can actually compose the work into something which is slightly nicer. And this is give and take a few places where I left out the parameter, how you could write things with the standard interface, where you basically say, all right, the magic over here is entirely in the core weights, which basically are places where the function runs up to the core weight. It starts the work, whatever that does. And once the work is complete, it resumes at the same point in the code. But while the work is outstanding, this coroutine is entirely inactive. It basically sits somewhere waiting just for being resumed later. And we just do that a few times over here, and then the whole thing completes. So this is kind of the cute way to write that. But this is what you need to write to basically a nice asynchronous version of the original code. If you squint, it's basically the same code we had in the beginning, and then we accidentally dropped a few co-weights in strategic places, and that is the entire change except for the return type. And all the magic happens via the return type. This is basically a coroutine thing. That's what I talked about 2 years ago, how to implement these guys, which arranges for all the asynchronous work to happen. All right. Now, the interesting bit is I entirely left out and claimed there is magic inside this black box. Now, let's look at how the black box could look like. And I start off with the newer and more interesting and more unfamiliar approach, which is actually easier than the other one. And this is for I/O. The idea is, well, all the black box really does is we basically, when we want to do some work with that thing, we say here's an operation and here's how we complete. The operation is basically consists of something like, literally for something like IOU ring, an opcode where you say IOU ring read or IOU ring write or whatever the operation is, plus a fixed set of parameters which may reference some memory which you point to, which you need to keep alive. But this is all no issue because we basically have an entity or a completion object where we wait for things to complete. And then all we tell the thing is, all right, dear context, this is basically, it's not called context, it's whatever IOU ring context or something like that, which you create with a suitable function. And then you call into that. It's a little bit, the context at doesn't quite look as simple, but conceptually it's just doing that. And then the operating system goes and does whatever it needs to comply with the, let's say, read operation or write operation. And it basically sends a completion saying, all right, this operation is now complete, and you just call into that. IOCP, IO completion ports on Windows, like IOU ring is Linux specific and recent versions of Linux. There's something which is way older, which is similar, however, which is IOCP, the IO completion ports in Microsoft. Is conceptually similar in the sense of you also say run things and it completes. The differences are in the details, more or less, although IOU ring is a way cooler interface. It's way cooler. Who has played with IOU ring? Anybody over here or just me? It's cool, right? Yeah. Yes. So we have one other person who has used it and it's great. Compared to all the other similar approaches, it's lovely. And then the way you basically complete things over here is, roughly speaking, this is not quite true for IOCP, but it's certainly true for IOU ring. You basically wait for things to complete, get the next completion, and effectively just call back into the function which gives back the result. So the black box, which I claimed is there and does things, is actually not that magical. If you don't have any of these things and you want to use older technology, you can use, basically, instead of a completion interface, use a readiness interface. This is, roughly speaking, things like, well, originally select. Hopefully nobody uses select anymore. Poll, yeah, maybe use poll, but nowadays people would probably rather use something like epoll or a KQ, and because the later ones are not available on Windows you don't use any of that, you use IO completion ports. So the idea over there is, in some sense, similar. You basically have lists of, except that you do things instead of telling the kernel do these operations, and it does roughly what we do over here outside the, what we do on the outside of the kernel, inside the kernel. We basically say, all right, we are interested in these file descriptors, and once there's activity on this file descriptor is ready to do the next step, let us know, and then the kernel will tell us, all right, Paul, basically call into Paul, the thread calling Paul will probably sleep until something happens, and that tells you, all right, these file descriptors are ready for this operation, and you basically go, all right, I waited for this file descriptor to read, so you read that file descriptor and call back into the completion. So either way, the main issue over here inside the black box is to do a little bit more fuffing about than just this, so that you can deal with all the file descriptors. You probably don't want to have just one poll running. If you have loads of file descriptors, you probably want to have multiple polls running, or you want to distribute them over multiple e-polls or whatever it is. So there's a little bit more complication really in technology to get it efficient, but it's not super magic. And all of these things, like the readiness model, is there since a long time. So select, I think, was fairly early Unix, and this exists since ages. It just gets improved. Okay, so going on to something which I haven't talked about yet at all, and this is when you normally run programs, you typically have two ways you run to an end. One is you complete successfully. This is hopefully the sunshine outcome you normally have. And the other one is you run an error. Now, I don't know why it does that. Now, if you kicked off work and now your control gets back to your core and you can do other things, you may find that some work you kicked off earlier is not relevant anymore. In fact, this is actually not such unusual case. The canonical example of where you find that some work is not necessary is often you want to not wait arbitrary amount of time until something happens. So you actually kick off two different asynchronous processes, one to do the actual work and the other one is a timeout. And you basically complete your actual work when one of them is finished and you cancel the respective other. Like if you wait for I/O, you typically go, right, I set up and wait for I/O for this amount of time. Typically the I/O happens and then you typically cancel the timeout you may have set as well. And then you rinse and repeat. So cancellation is a really common thing. And cancellation is one of the more interesting things inside the black box. To basically what you do inside there, roughly speaking, is you find the outstanding operation, you remove it if it is something like a poll. If it is IU ring or IOCP, you actually need to tell the system, actually complete the thing, please, with a cancellation. And then these systems already readily complete this cancellation and tell you, all right, yep, this thing is now canceled. So you basically always get a response back to any of these requests. And this is how cancellation works. But cancellation in an async system is super important. So this is actually something which needs to be built into the system and should work just smoothly and in a natural way. Okay, so yeah, the example, the canonical example, there are other examples, but waiting for input taking too long, and you use a timer to indicate that. The other thing where cancellation is obviously a place you want is if you want to shut down your system. Right, your system is happily running and everything is fine, but you go, actually, I would like you to shut down. Now, if you wait for input from a user, this may take arbitrary amount of time and you probably don't want to wait that long. So basically just go, please cancel, and so you can shut down the entire system. But yeah, cancellation, complete that, cancel that, or other way around. Okay, going on a little bit more on the what does the standard do. So the standard interface, how we want to represent asynchronous work in the future in C++, is basically the core idea is called senders. It normally is referred to as senders and receivers, but user code normally doesn't see receivers directly. Receivers are only needed if you only need to meddle with them if you actually implement senders. So the idea of a sender is it's an object representing work. For example, do an I/O request and write the result into this buffer, or wait for this amount of time, or execute this computation on a different CPU. And examples from what we had earlier, receive request, read file, send response would be senders. There would not be senders which the standard library would provide, but they would probably be built on top of other facilities to basically take what lower level things are there to compose the higher level work. The general, or not the general, senders but are lazy. That is, if you create a sender, it actually doesn't do anything. It just sits there and is basically representing work without doing any work. I mean, this is me at work. Right? You tell me, all right, I'm not doing anything. Eventually somebody comes and says, can you please produce a result to him? Okay. And eventually I get back to them. But senders are just the same. And this allows composition of work, which is nice, right? This is what I do at work as well, right? If people come to me, I go kind of, oh, what if I compose the work of my teammate with the work of this teammate, and then I package this up and tell them, here's the result. I don't take credit. I typically say, these two guys did it, but the same over here, right? You basically have other lower level work, and you basically build that up into different workflows. And then each workflow itself becomes a sender, and you basically go, right, you just build higher level senders. For the workflow example, for example, the received request, if I want to break it down into something which is still not lowest level, I probably have a client which internally has a buffer, and I want to read up to, let's say, \n, this is what represents where the request ends. I cannot expect the operating system to read up to \n. They don't do that. They basically do things like, yes, you read and you give me a buffer, and here's how many bytes you read. So I probably need a little bit of buffering so that I don't overread beyond, in case somebody sends a request for 2 cat images separated by a new line, and I get that as one package back from the operating system. So I probably need something like a buffer inside, but this we could implement as well. And then the actually asynchronous approach is really just the red thing over there. We read a buffer, and the rest is hopefully kind of correct. The idea is first time the buffer is empty, we don't find anything. What we didn't find, we insert into the name, then we wait for whatever we read, and this tells us how much it actually read. Once we have read nothing, we go kind of, well, we're done, we didn't find anything. And then we insert, well, in which case we fail, and otherwise we read more. But this is basically just saying, right, we can package these things up and we can create new things. We can build the next thing on top of received request. This uses a coroutine. None of these things do require the use of coroutines. Like the sender interface can very well just be composed differently. It just becomes more annoying. It becomes probably more efficient, but it's also more annoying to write. And whether it's really that much efficient, I don't know. I haven't measured that yet. So the completion, before I kind of pretended and squinted this is looking like a function call. In the sender-receiver world, a receiver is the entity which receives results, and it's actually a generalization of a function. It basically, the function call bit is the first call over there, set value, which is called when the operation is successful. We basically can provide multiple results. This could be something like, yeah, whatever it is, whatever the operation needs to produce, it can produce multiple arguments and say these are the successful results. Or it can be an error, in which case, you know, right, we finished with an error. Separating these channels into a success and an error, and then the third one for the set stop for cancellation, has a nice advantage that if you write an algorithm, you don't need to figure out, is this result an error or a cancellation? You know, you get told this was an error. So you can basically have an algorithm which goes, all right, I waited for multiple operations, one errored out. If it errored out, I can cancel the others, for example. Whereas if it succeeded, I need to wait for all the others to succeed, and then I succeed, or something like whatever it is. But knowing how the operation completed allows you to, like in which kind of completed, allows you to write algorithms which are generic without knowing anything about the details. And then the last thing over here, the get end, that's an interesting one. This is something which functions often don't have. Some of the completion things do have something like that. The idea over here is we can pass in something from the receiving end, we can pass in a parameter into the asynchronous operation we want to execute. Now, what kind of parameters do you want to pass in? An example is the indicator whether we want to cancel. This would be a stop token. So you basically go, like an async operation could go, like a read operation could go and say, all right, I will set up that I read, but if I'm asked to stop, I need to somehow arrange for that. And to do that, you can ask for a stop token from your environment and say, all right, this is a stop token for read operation because it doesn't do any work. We probably want a callback once the stop token, well, the stop token receives a stop request. So stop token and is basically associated with stop source. Somebody asks a stop source to stop, which will cause a stop token to say, oh, please stop, which is you investigate that, but it also triggers a callback to say, all right, please call that function. And this is important. The callback is important for things which don't do any work, because if you have a read operation, nothing is waking us up to do things to look at whether we got stopped, unless we have something which calls us. This is where the callback comes in, so we can go and tell our context, oh, we got stopped, please remove us. For things which do computations, where you basically have a tight loop of you compute things, you may have a stop token and ask the stop token once in a while, should I stop? Should I carry on? Should I carry on? Should I carry on? Right, this is, well, we do that at work as well. Do we really need that work done? Now eventually they give up. So this is basically the receiver. You normally don't see that, but it's nice to know that it's there. So if you want to write an algorithm, yep, quite easy. And then, now the interesting bit is, I talked about there's a receiver and there's a sender. A lot of async interfaces I've seen don't do that, but sender-receiver, basically you have these two independent things and you bang them together to basically say, we get a new entity, which is actually the ready-to-run state representing the completion and the necessary work. And this is what's called a connect operation, where you connect a sender to a receiver and you get a state out. One thing which is interesting about the state is expected not to be moved. That means the operation can have basically pointers into the state and channel these things chain these things together, which is actually really valuable because you don't need to allocate any state to say, please call into the things and complete over here, which goes away and you only allocated it to stay put. The return object coming from connect does that, which actually is a little bit related to what Michel talked about earlier. This is requiring guaranteed copy elision. Without guaranteed copy elision, you couldn't do that. Over here, you can do that because you know this object cannot be moved, it cannot be copied, but it can be returned, which means you typically do that on a return statement. And then once we have such an object, we can start it. And this is where now finally work happens. We have basically set everything up and eventually we start something. And this probably, if there's composed work, the start on the outer thing probably starts some work on inner objects, and once these complete, other things get started. So this is not just necessarily just one start, it probably results in multiple other starts, but on every level, it looks from the outside just we start the state and then we get a result. And this is where another really important part comes in, and this is kind of the sender-receiver contract. And the idea is any operation, well, if you have an operation which starts sub-operations, the guarantee is that all sub-operations have completed before the outer guy completes. This means there's basically a scope of when does that work happen. And then the opposite direction is any operation state which gets started will eventually complete with exactly one completion on basically a receiver which is moved. But So it will always call a set value, set error, or a set stopped if the system is running. Obviously, if you go and kill -9 the process, that this contract cannot be obeyed. But in a running process, the view is always kind of, once we have started something, it has to complete. And it just does that. This is essentially taking these two operations or these two parts of a contract together, yielding something which is called structured concurrency, where you basically structure your concurrency in a way where basically everything is nested. Now, the obvious question which immediately came into my mind is kind of, how does that work if I want to create new work? Right? I get in, let's say I have a server, I accept the connection. And now I want to start something. But while I start this is kind of, once I've started that, this guy finishes and waits for the next thing. The answer to that is, you actually do not start operations necessarily inside the entity you are in. Instead, you may have, and this is one of the components that we have, you may have a scope where you go and take in the work and say, dear scope, please start that thing and hold on to it until it's finished. And then it becomes the scope's problem to provide the nesting. And there's less of a problem, because all the scope does is say, all right, cool, here's more work for me to do, and I will stay alive while there is outstanding work. And I complete, or I provide something which can complete once everything I'm waiting for, everything I started, actually completes. Okay, so this is kind of the fundamental idea behind all of it. Just to give an idea why we do some of these things, and this is, it allows to implement algorithms which are actually kind of hard to do. Well, they're not super hard, but if you do them over and over, it becomes annoying and hard to do certain things. For example, a when-all operation, where you basically go, I want to, let's say I get a request and I need to ask this database and this other service, and once I get these two results back, then I can complete. We could do these things sequential, then we don't need anything like when-all, but if these are actually independent, we can kick them off concurrently and just combine them once we are back. And we can quite easily implement something like a when-all operation. I'm not saying that it's, oops. Okay, this time I press. It's not as easy that I could just show you how to implement it in 10 minutes or something like that, but implementing when-all takes maybe a day. Once somebody has implemented when-all, nobody else needs to implement a when-all with exactly the same semantics. They can just use it. And the idea, all it does is it produces a result of basically a tuple of all the results of the different senders. And if one of them fails, it cancels all of them. Or it cancels. You can also get canceled. And then the other thing, this is unfortunately not in C++26, and we don't know what. The question is, why is that not in there? Yes, I don't know. This is actually the really important one. I know why it's not there, I think. So the question from the audience is kind of what? Why is not when any not there? Well, if you do networking, when any is absolutely what you need and want. But if you do compute, which is what drives a lot of the sender-receiver stuff, you don't really need that. You need more when-all than when-any. I think this is part of the reason why we don't have when-any. So the idea of when-any is kind of similar to when-all, but instead of waiting for all of them to complete, you go, I wait for the first one to complete, and I complete with that completion, and I cancel all the others. Which may mean, by the way, if you get one result and start canceling the others, you may actually get a successful result from the others. But you will ignore them. Or you have a different when-any. You can have a when-any which collects all the guys it succeeded. But if you have something like when-any, implementing a timeout is really easy, right? It's an algorithm. We resume after time or work, and we basically cancel otherwise. It's a little bit fuffing about to say we probably want to turn the resume into an error completion. So it's not quite as easy, but roughly speaking, this is what it is. And then to basically talk a little bit about how does a real application look like. Typically, it's relatively straightforward, I think, and that is you set up some kind of context where you live, which could be an I/O context for something which is I/O-based, or a thread pool, or both. And then you basically start off with the initial work, which may spawn other work, and you probably set up something like a counting scope to contain all the dynamically created work. And then you just kick it off and wait until it is done. So if we go and say we have our cat server from earlier, this could be basically running the actual server. This is just going, right, we accept some, we basically create a port where people connect, and then whenever we have the async accept return something, we basically kick off another client. And we basically chuck that into the scope. Again, it's not quite as easy. There's a little bit of reasons why it's a little bit more complicated, but roughly speaking, that's it. And our main, basically, like I said, we set up an I/O context, we set up a counting scope, we spawn. Spawn does not create a thread. All spawn does is it tells a scope, and I forgot to say token, but still roughly is correct. We spawn our run server thing, which basically starts it over there and holds on until it completes. It doesn't do any work. Actually, no work happens over here until we call in the bottom sync wait. And sync wait is something probably every program will have one call to sync wait, but hopefully it's the only one. And this is in main where it goes kind of, we wait until everything is done. And the things we run over here is we run the context and we run the scope upon empty, which is basically saying, right, the scope finished, it's empty, we can complete. And that's that. Okay, and with that, I want to point at the resources I have, and this is what I want to talk about. So, anybody having any questions? Or?
Very much. Questions?
Oh, no.
Oh.
If there are no questions, it means I need to come back and do a more basic talk. Because I lost everybody. Well, either that or everybody tells me this was awesome, we really got it, which I don't believe in.
I have one question.
Okay.
So, if I followed correctly, what we still are missing is a standard way of doing the last part, which is waiting asynchronously from the input-output, right?
Yes. We have no way to wait in the standard yet how to wait for I/O. We currently also don't have something like a thread pool where you could put work into. We have the infrastructure to do all of these things. We may get a thread pool to put work into, but we also don't have the work yet, as far as I know.
Okay.
Which is embarrassing.
What we do not expect by no means is to have a standard way for the I/O, right?
Correct. I/O will not be part of C++ 26. This hopefully comes in 29, but we will see whether this happens.
In 29, it will come for networking, hopefully.
Yes.
What about this I/O?
What about files? What about keyboard?
Yeah. I was very specifically thinking on disk I/O.
Or disk I/O, okay. So asynchronous disk I/O is, as far as I know, interesting in the sense of there's, as far as I know, from what I gather, there's one properly working system which does it, which is IO Uring. This is actually why IO Uring was created.
Yeah.
But I'm not aware of anybody working on exposing that as a standard library. The person who did work in that direction is going away, as far as I know.
Okay.
So I don't know, and he did not intend to do an sender-receiver interface. I'm not an expert on any of that. I'm also not an expert on networking for that matter. I still try to take that on.
Come on.
I'm not. I'd still try to take that on. I'm not sure whether I will manage to do file I/O. I could imagine more things like a keyboard, like standard in, standard out thingy,
Okay.
which would also be a win. We don't have that either. But whether I can do file I/O platform, cross-platform, I have no idea.
Okay. And how do you feel are the chances that we get networking for 29?
I go with non-zero.
Okay.
I'm not placing it close to 1 necessarily, because it's a lot of work, and people have ideas. And the problem with people having ideas is not everybody who has ideas does the work. So if everybody who had ideas actually did the work, some of these ideas would not come, and other ideas would come, and they could just be taken on. But if people basically go, oh, yeah, that's good enough, but we absolutely also need that, this can delay things. You know the standards process.
I know a little bit. So I'm specifically insisting in this because over the lunch, I got the question, will I get networking before I retire?
But you? I don't know about
not
your
me,
age.
Not me. No, I'm tied to retiring whenever we get rid of the preprocessor.
Okay. There you go. So I do hope that I get networking before I retire, which is actually possibly sooner than you, but I don't know.
Can you go to the last slide, please?
Sure.
Okay, yeah, previous to the last one. This one. So I'm not understanding, I'm not following you. So
okay.
You mean that all of this is not going to be standardized?
Okay. No.
So well, not IO context, spawn, sync wait, nothing?
So, well, okay, let's go with every other line is standardized. Okay. So IO context is not standardized. You can get an implementation with the basic IO system from Beeman. It's there. If you go to Beeman.net, there is an implementation. The counting scope is standardized or is getting standardized. The spawn with the thing is actually also getting standardized. Well, actually, not every other, just the IO context is kind of missing. Yeah.
Okay. So for example, sync wait is going to be standardized.
Sync wait is in the standard already, as is when all the context run. This is something which comes from IO context, which is not standardized yet, and the scope upon empty is also in the standard. So most of that thing, except for the IO context, is kind of there.
Okay. And just out of curiosity, this sync wait can be called using several threads? Can I call this sync wait, or that depends on the IO context? So can I call sync wait in? Yeah. Can I
sync wait does not depend in any shape or form on IO context. It basically all it gets is a sender. It does not take arbitrary senders. It needs to have a little bit of a shape.
So then maybe it's context run, what I'm asking. So can I run context run in several threads? So I want to put several threads into the work.
Well, okay. I imagine that to be working. This depends on how the context is defined. So I cannot, I don't know yet, sort of, but I imagine that you can contribute multiple threads to the context and run them. And then you would have basically, over here, the sync wait running the context itself is basically making sure that I use the one thread I have, the main thread, to run the context as well as all the other work. This is what's happening with event all over there. This is just kind of a sort of a hack to not run another thread.
Thank you for the talk. I want to talk about. I want to ask you about networking implementation again. So, in which way do you have in mind to be implement networking? So it will be a barrier for new joiners, or it will be implemented in such a way that only experted people can use it.
I expect that it is really easy usable. I expect it to be, personally, I expect it to be easier to be usable than ASIO by a long shot. And in fact, if you go to my presentation on CPPCon, where I create an HTTP server live in an hour, you can see what it takes at the moment. This does not really take the interface into account which we envision, which is at the moment is more like an async abstraction similar to ASIO level, where the standards committee actually wants an abstraction which is more along the lines of IETF tabs, which is way higher level and way more complicated, but you would actually get an easy way to create an TLS socket. So the intention over there is, or the reason the standards committee wants to use tabs is primarily to say we want to, the easiest way to create a client socket should be a TLS socket, so that users actually, like newcomers, would actually need to do extra work to not get a secured socket.
Security by default.
Yes, absolutely, security by default. You can get one which is not doing that, but you will need to do extra work. You need to say, all right, don't do security, and don't do that, and don't do that, and then you get what you currently get as a default, so we need to swirl them around.
Good. Questions? More questions?
Okay.
It was a long day, so thank you very much.
Thank you.